Electrical fuses explained. Electrical fuses are devices used to protect electrical circuits and equipment from overcurrent conditions, such as short circuits and overloads. When the current passing through a fuse exceeds a predetermined threshold, the fuse blows, meaning it melts or breaks, interrupting the circuit and preventing further current flow. This action helps prevent damage to the connected devices and reduces the risk of fire hazards. Here's a more detailed look at electrical fuses. The fuse element is a critical component within a fuse that plays a fundamental role in the device's function. It is the part of the fuse that is designed to melt or break when an excessive current flows through it. This action interrupts the circuit and prevents further current from passing through, thereby protecting the connected equipment and wiring from damage due to overcurrent conditions. Key characteristics and features of the fuse element include: material. Fuse elements are typically made from materials with low melting points and high electrical resistance. Common materials include various metal alloys such as tin, lead, copper, and silver. Low melting point. The fuse element material is chosen for its low melting point compared to the expected normal operating current. This ensures that under overcurrent conditions, the element will melt before the excessive current causes damage. Heat generation. When current flows through the fuse element, it generates heat due to the resistance of the material. This heat causes the element's temperature to rise. Melting and breaking. As the current increases beyond the fuse's rated capacity, the heat generated by the element increases. At a certain point, the heat causes the element to melt or break, creating an open circuit. Blow curve. The relationship between the time it takes for the fuse element to blow and the magnitude of the overcurrent is defined by the fuse's blow curve. This curve helps engineers and designers understand how the fuse will respond to different levels of overcurrent. Size and shape. The size and shape of the fuse element influence the device's current carrying capacity and response characteristics. Larger fuse elements can handle higher currents, but they might take longer to blow under overcurrent conditions. Construction. The fuse element is often a slender wire or strip of the chosen material. Its design and dimensions are critical to ensuring that it responds appropriately to overcurrents and that it melts or breaks in a controlled manner. It's important to select a fuse element with properties that match the intended application. The element's melting point, material properties, and physical dimensions must be chosen carefully to ensure that the fuse offers reliable protection while preventing false or premature blowing during normal operating conditions. Properly designed fuse elements contribute to the safety and longevity of electrical systems by preventing damage from overcurrent events. The fuse body is an essential component of a fuse, providing physical protection and insulation for the fuse element and contributing to the overall safety and functionality of the device. It encases the fuse element and helps ensure that the fuse operates as intended, both electrically and mechanically. The fuse body is designed to prevent accidental contact with live parts and to contain any arc or debris that may result from the fuse blowing. Key aspects of the fuse body include: protective casing. The fuse body is typically made from non-conductive materials such as ceramic, glass, or high-temperature plastics. These materials offer electrical insulation, preventing unintended electrical contact. Insulation. By enclosing the fuse element within the fuse body, the risk of short circuits or unintentional contact with the live components of the fuse is minimized. This insulation helps maintain a safe operating environment. Mechanical strength. The fuse body provides structural support and mechanical integrity to the entire fuse assembly. It protects the fragile fuse element from physical damage that could lead to premature blowing or other issues. Temperature resistance. The fuse body is designed to withstand the heat generated during normal operation and the extreme temperatures that can occur when the fuse blows due to overcurrent. This ensures that the fuse remains intact and safely contained. Clear markings. Many fuse bodies have markings indicating the fuse's current and voltage ratings, breaking capacity, and other important information. These markings help users select and replace fuses correctly. Form and shape. Fuse bodies come in various shapes and sizes, depending on the specific fuse type and application. For example, cartridge fuses have cylindrical bodies, while blade fuses have rectangular bodies with blade-like terminals. Arc containment: in the event of a fuse blowing due to a short circuit or overload, an arc might be produced. The fuse body helps contain this arc, preventing it from causing additional damage or hazards. Environmental protection: the fuse body shields the fuse element from external contaminants, moisture, and other environmental factors that could impact the fuse's performance. The fuse body, together with the fuse element and other components, creates a complete fuse assembly that is engineered to protect electrical circuits and equipment from overcurrent conditions. Properly designed fuse bodies contribute to the safety, reliability, and longevity of electrical systems by ensuring that the fuse operates effectively under various conditions. The rating information of a fuse provides important specifications and characteristics that help users and engineers select the appropriate fuse for a particular application. These ratings ensure that the fuse will operate safely and effectively within the intended electrical system. The rating information is typically marked on the fuse body or packaging and includes several key parameters. Current rating, amps: this is the maximum current that the fuse can carry continuously without blowing. It indicates the fuse's current carrying capacity and helps prevent the fuse from overheating under normal operating conditions. Voltage rating: volts: the maximum voltage at which the fuse can operate safely without arcing or insulation breakdown. It ensures that the fuse can handle the voltage present in the circuit. Breaking capacity: interrupting rating: this value indicates the maximum fault current that the fuse can safely interrupt without causing damage to itself or posing a safety risk. It's important for fuses used in circuits where high fault currents can occur. Time current characteristic: TCC fuses have specific time current curves that show how long they take to blow at different levels of overcurrent. These curves help engineers choose the right fuse for a given application by considering the balance between protecting the circuit and allowing temporary overcurrents. Operating class: fuses are often categorized into classes based on their time current characteristics and intended applications. Common classes include fast acting, F, time delay, T, and medium time delay, M. Temperature ratings: fuses can be rated for specific temperature ranges to ensure they operate reliably in different environments. For example, temperature ratings might include normal, high, or very high ambient temperatures. Physical size and form factor: the dimensions and shape of the fuse are also important considerations, especially when space constraints are present in the application. Application recommendations: some fuses might have additional notes or recommendations regarding their suitable applications, specific industries, or other relevant information. It's crucial to carefully match the fuse's ratings to the requirements of the circuit or equipment it will protect. Choosing a fuse with incorrect ratings could lead to inadequate protection or unnecessary blowing of the fuse under normal operating conditions. Consulting the manufacturer's datasheets, guidelines, or working with a knowledgeable professional can help ensure that the correct fuse is chosen for a specific application. The current rating, expressed in amperes, is one of the most important specifications of a fuse. It indicates the maximum amount of current that the fuse can safely carry without blowing or melting its fuse element. The current rating of a fuse is determined based on the capacity of the connected circuit or equipment it is intended to protect. Here's how the current rating works. Maximum current: the current rating indicates the highest current that the fuse can continuously carry without tripping or blowing. This means that as long as the current flowing through the fuse is below its current rating, the fuse will remain intact and allow the circuit to function as expected. Overcurrent protection: if the current passing through the fuse exceeds its current rating, the fuse element will heat up due to its electrical resistance. If the overcurrent persists and reaches a critical point, the fuse element will melt or break, interrupting the circuit and preventing further current flow. This action protects the connected equipment and wiring from damage caused by excessive current. Matching the application: when selecting a fuse for a particular circuit or equipment, it's crucial to choose a fuse with a current rating slightly higher than the expected normal operating current. This provides a safety margin while allowing the circuit to function properly under typical conditions. Inrush current. In some cases, circuits experience a temporary surge in current during startup, known as inrush current. The fuse should be able to handle this inrush current without blowing. Therefore, the inrush current characteristics of the circuit or equipment should be considered when selecting a fuse. Selecting the right current rating. Choosing a fuse with an appropriate current rating prevents nuisance blowing of the fuse during normal operation while ensuring effective protection against overcurrent events. Using a fuse with a too low current rating might lead to frequent fuse blowouts, disrupting the system, while using a fuse with an excessively high rating might compromise the circuit's safety. It's important to note that fuses are available in various current ratings, so it's essential to choose the rating that matches the specific requirements of the circuit or equipment. Consulting the circuit specifications, guidelines, or working with a knowledgeable professional can help ensure that the correct current rating is selected for the fuse to provide effective protection. The voltage rating of a fuse, measured in volts, is a crucial specification that indicates the maximum voltage at which the fuse can operate safely without arcing, insulation breakdown, or other electrical hazards. The voltage rating of a fuse is determined by the circuit or equipment it is intended to protect. Here's how the voltage rating works. Maximum voltage. The voltage rating specifies the highest voltage that the fuse can be exposed to without causing the fuse to fail or pose a safety risk. This ensures that the insulation properties of the fuse and its housing remain effective even under high voltage conditions. Voltage endurance. Fuses are designed to withstand normal operating voltages and possible voltage fluctuations that can occur in electrical systems. If the voltage exceeds the fuse's rating, it could lead to arcing or insulation breakdown, which might compromise the fuse's ability to protect the circuit. Matching the application. When selecting a fuse, it's essential to choose one with a voltage rating that matches or exceeds the maximum voltage that the circuit or equipment can experience. Using a fuse with a lower voltage rating than the circuit's requirements can result in safety hazards and reduced reliability. Overvoltage protection. In some cases, circuits might experience voltage spikes or transients that exceed the normal operating voltage. Fuses with higher voltage ratings might be chosen to provide an extra margin of safety against such transients. Multi-voltage systems. In systems with multiple voltage levels, different fuses might be needed to protect circuits operating at different voltage levels. Environmental factors. Environmental conditions such as temperature, humidity, and pollution levels can influence the performance of a fuse's insulation properties. Some fuses might have derating factors to account for specific environmental conditions. It's important to carefully consider the voltage rating of a fuse to ensure that it can effectively protect the circuit or equipment from overvoltage situations. Using fuses with voltage ratings that are too low can lead to electrical hazards, equipment damage, and reduced system reliability. If there is uncertainty or specific concerns regarding the voltage conditions in a circuit, consulting guidelines, datasheets, or professionals in the field can help ensure the correct fuse is selected for the application. The breaking capacity, also known as the interrupting rating, of a fuse is a critical specification that indicates the maximum amount of fault current that the fuse can safely interrupt without causing damage to itself or posing a safety risk. It is a crucial parameter, especially in systems where short circuits or high fault currents can occur. The breaking capacity of a fuse is determined by the capabilities of the fuse element and the fuse design. Here's how the breaking capacity works. Short circuit protection. Fuses are designed to protect circuits and equipment from the potentially damaging effects of short circuits. A short circuit occurs when a low resistance path is created between 2 points in a circuit, allowing an extremely high current to flow. Interrupting high fault currents. In the event of a short circuit, a high fault current can flow through the circuit. The fuse must be capable of interrupting this fault current quickly and effectively to prevent further damage or hazards. Fuse element strength. The fuse element's material and design contribute to its ability to interrupt fault currents. A properly designed fuse element can withstand the mechanical and thermal stresses caused by high fault currents without disintegrating or posing safety risks. Matching system fault currents. The breaking capacity of a fuse should match or exceed the maximum fault current that the connected system can produce. This ensures that the fuse can safely interrupt the fault current and protect the circuit. System design considerations. The breaking capacity is particularly important in systems with high fault current potential, such as industrial power distribution systems. In these cases, the fuses must be selected to handle the maximum fault currents that can occur. Coordinated protection. In complex systems, it's important to coordinate the breaking capacities of fuses, circuit breakers, and other protective devices to ensure that the fault current is interrupted by the appropriate device. Choosing a fuse with a breaking capacity that is lower than the expected fault current can result in catastrophic failures, including fuse explosions and hazardous conditions. Therefore, it's crucial to consult electrical system specifications, conduct fault current analysis, and work with professionals to ensure that the fuses selected have adequate breaking capacities for the specific application. Properly chosen fuses contribute to the overall safety and reliability of electrical systems. The time current characteristic, TCC, of a fuse, also known as the time current curve, is a graphical representation that shows how long a fuse takes to blow or interrupt the current at different levels of overcurrent. The TCC provides valuable information about the fuse's response time under various fault conditions. Understanding the TCC helps engineers and professionals select fuses that offer the right balance between protection and allowing temporary overcurrents. Here's how the TCC works. Response to overcurrent. The TCC graphically shows how quickly a fuse will operate when subjected to different levels of overcurrent. It demonstrates the relationship between the magnitude of the fault current and the time it takes for the fuse to blow and interrupt the circuit. Vertical axis, current. The vertical axis of the TCC graph represents the fault current in multiples of the fuse's current rating, also called multiple of rating or XIN. It indicates the severity of the overcurrent condition. Horizontal axis, time. The horizontal axis represents the time it takes for the fuse to blow under the specified overcurrent conditions. This axis is usually logarithmic to allow for clear representation of both fast blow and time delay characteristics. Curve shape. The curve on the TCC graph represents the fuse's response to overcurrent. Different types of fuses, fast acting, time delay, etc., have distinct curve shapes, indicating how they react to various fault currents. Curve types. There are generally three main curve types. Fast acting, F. These fuses blow quickly when the fault current exceeds a certain level, providing rapid protection against short circuits. Time delay, T. Also known as slow blow or time lag fuses, these have a delay before they blow, allowing for temporary overcurrents, such as motor starting currents. Combination, K or D. These fuses combine characteristics of both fast-acting and time-delay fuses, providing a balance between quick response and accommodating temporary overloads. Coordination, TCCs are used to ensure proper coordination between fuses, circuit breakers, and other protective devices in an electrical system. This coordination prevents unnecessary tripping or blowing of upstream protective devices when a fault occurs downstream. Understanding the TCC of a fuse helps engineers make informed decisions about selecting the right fuse for a specific application. By analyzing the TCC in relation to the expected fault currents and the equipment's characteristics, engineers can ensure that the chosen fuse provides effective protection without causing unnecessary disruptions in the system's operation. Operating class refers to the categorization of fuses based on their time current characteristics, specifically how quickly they respond to overcurrent conditions. Different operating classes correspond to various response times, which makes it possible to select a fuse that aligns with the protection needs of a particular application. The operating class of a fuse is denoted by a letter code, and each letter corresponds to a specific response characteristic. Here are the common operating classes for fuses. Fast-acting, F. Fast-acting fuses are designed to blow quickly when the current exceeds a certain threshold. They provide rapid protection against short circuits and are often used to safeguard sensitive electronics or equipment that needs immediate protection. Time delay, T. Time delay fuses, also known as slow blow or time lag fuses, have a built-in time delay before they blow. This delay allows the fuse to tolerate temporary overcurrents, such as those caused by motor starting currents or inrush currents. Time delay fuses offer a balance between protecting against faults and accommodating normal transient current spikes. Medium time delay and medium time delay fuses fall between fast-acting and time delay fuses in terms of their response characteristics. They offer a moderate time delay to accommodate moderate overcurrent conditions while providing better protection against short circuits than time delay fuses. Ultra-rapid ultra-rapid fuses are designed to respond very quickly to overcurrent conditions. They provide an even faster response than fast-acting fuses, making them suitable for applications where extremely rapid fault clearing is required. High-speed high-speed fuses are designed to provide fast protection against high fault currents. They offer a balance between fast-acting and ultra-rapid fuses, making them suitable for applications that require a quicker response than typical fast-acting fuses. Very fast-acting very fast-acting fuses provide a response time between fast-acting and ultra-rapid fuses. They are often used in applications where a quick response is necessary without being as rapid as ultra-rapid fuses. The choice of operating class depends on the specific requirements of the circuit or equipment being protected. Different components within an electrical system might have varying sensitivities to overcurrent events. By selecting the appropriate operating class, engineers can ensure that the fuse responds in a manner that provides effective protection without causing unnecessary disruptions to the system's operation. Temperature ratings for fuses indicate the range of ambient temperatures in which the fuse can safely operate while maintaining its intended performance characteristics. These ratings are important because fuses are subject to various environmental conditions, and their thermal properties can affect their behavior and reliability. Temperature ratings help ensure that fuses operate reliably across different operating conditions and prevent unintended fuse operations due to temperature-related factors. Here's how temperature ratings for fuses work. Ambient temperature. The temperature rating specifies the range of temperatures in which the fuse can operate effectively. This includes the temperature of the surrounding environment where the fuse is installed. Normal operating conditions, fuses are designed to function optimally within a specific temperature range. Operating within this range ensures that the fuse's thermal properties and response times remain consistent. Derating factors. In environments where the ambient temperature is higher than the fuse's rated temperature, derating factors might be applied. Derating involves reducing the fuse's current carrying capacity to compensate for the increased temperatures. This ensures that the fuse operates safely under elevated temperature conditions. High temperatures. Fuses can experience increased heat due to factors such as nearby heat-producing components, enclosed spaces, or high ambient temperatures. Choosing fuses with appropriate temperature ratings prevents overheating and potential damage. Low temperatures. Extremely low temperatures can affect the performance of some fuses, particularly those with sensitive elements. In such cases, choosing fuses with appropriate low temperature ratings ensures reliable operation. Environmental conditions. The fuse's environment, including factors like humidity, air circulation, and pollution levels, can impact its thermal performance. Some fuses might have additional environmental ratings to account for these factors. Application requirements. Different applications might have specific temperature requirements. For example, industrial environments might have different temperature considerations than residential settings. When selecting fuses, it's important to consider the temperature conditions where the fuses will be installed. Ensuring that the chosen fuses have suitable temperature ratings helps maintain their reliability and effectiveness in providing overcurrent protection. If you're unsure about the temperature requirements for a specific application, consulting fuse datasheets, guidelines, or professionals in the field can provide valuable insights. The physical size and form factor of a fuse refer to its dimensions, shape, and overall design. These attributes play a crucial role in determining how the fuse can be installed, integrated into a circuit or system, and its compatibility with existing components or fuse holders. The physical size and form factor are important considerations when selecting fuses for specific applications. Here's how the physical size and form factor of a fuse work. Dimensions. The physical size of a fuse includes its length, width, and height. Different fuses come in various sizes to accommodate different current and voltage ratings, as well as to fit within specific spaces. Shape: fuses can have different shapes, such as cylindrical, rectangular, blade type, or cartridge style. The shape often corresponds to the fuse's intended application and the type of fuse holder used. Termination style: the way the fuse connects to the circuit or holder is also important. Some fuses have axial leads, while others have radial leads, blade terminals, or other specialized terminations. Fuse holders: fuses are often installed in fuse holders or fuse blocks. The physical size and shape of the fuse need to match the corresponding fuse holder to ensure proper installation and secure connection. Space constraints: in some applications, there might be limitations on the available space for installing fuses. Choosing fuses with appropriate sizes ensures they can be accommodated within the available area. Clearance and creepage: electrical safety standards often dictate the minimum distances, clearance and creepage, between conductive parts, including fuses. The fuse's physical size and shape should comply with these standards. Installation and replacement: ease of installation and replacement is influenced by the form factor. Fuses that can be easily inserted, removed, and replaced simplify maintenance and reduce downtime. Stacking and arrangement: in certain scenarios, multiple fuses might need to be stacked or arranged closely together. The fuse's physical size and design should allow for this arrangement without compromising safety or functionality. The physical size and form factor of a fuse should be considered alongside other specifications, such as current rating, voltage rating, and breaking capacity. Choosing the right size and shape ensures that the fuse can be properly integrated into the system and provides effective protection without causing compatibility or installation issues. When selecting fuses, consulting datasheets, guidelines, or professionals can help ensure that the chosen fuses are suitable for the specific application's physical requirements. Application recommendations for fuses provide guidance on the suitable uses and scenarios where a particular type of fuse is best suited. These recommendations help users and engineers make informed decisions about selecting the right fuse for a specific application. The recommendations take into account the fuse's characteristics, response times, and other factors that impact its performance in different situations. Here's how application recommendations for fuses work. Specific industry requirements: certain industries have unique requirements that dictate the type of fuses needed. For example, automotive, industrial, residential, and aerospace applications might have different demands in terms of current levels, voltage ratings, and response times. Load types: different types of electrical loads, such as resistive, inductive, and capacitive loads, can influence the type of fuse that's appropriate. For instance, motors and transformers might require fuses with specific time delay characteristics to handle starting currents. Sensitivity: some electronic components and circuits are more sensitive to overcurrents than others. Fuses with fast-acting characteristics might be recommended for circuits where rapid protection is necessary to prevent damage to sensitive components. Motor protection: motors often experience higher inrush currents during startup. Fuses with time delay characteristics can prevent unnecessary tripping during motor starting, ensuring smooth operation. Circuit characteristics: the overall behavior of the circuit, including load fluctuations, transient conditions, and peak currents, can impact the choice of fuse type and rating. Short circuit protection: high fault current potential requires fuses with appropriate breaking capacities to handle short circuit events without endangering personnel or damaging equipment. Coordinated protection: coordinating the protection of fuses with other protective devices in the circuit, such as circuit breakers or contactors, ensures seamless and reliable operation. Environmental factors: harsh environments with high temperatures, humidity, or chemical exposure might require fuses with enhanced environmental ratings. Specific applications: certain applications might require specialized fuses. For example, automotive fuses are designed to withstand vibration and other automotive conditions. Regulatory compliance: fuses used in specific applications, such as medical equipment or aerospace systems, might need to meet specific regulatory standards. Application recommendations help guide fuse selection by providing insights into where certain fuse types excel and what scenarios they are designed to handle effectively. By considering these recommendations, engineers and users can choose fuses that offer the right balance between protection and operational requirements, ensuring optimal performance and safety within their specific applications.